All right. Today we are going to start Unit 3. We're going to start talking about the periodic table and its organization. So before we start, I'm going to give you a brief history of the periodic table. And when I say brief, you may not think it's all that brief because might take a while, but brief as in I'm not going to get into absolutely everything about how the periodic table was created and how the periodic table came to be. We're just going to kind of hit the high points of the creation of the periodic table. And then in later notes, we will talk about how it's organized and all of that. So today we're going to talk mainly about the history of the periodic table. So before we get into that, though, we do want to talk about the classification of the different types of elements on the periodic table. There are lots of different elements. There's 118 of them. But they fall into three categories, all right? So substances, as you remember from way back in Unit 1, substances are either elements or compounds. All elements are on the periodic table, and compounds are chemical combinations of different elements. So elements are going to fit into these three categories. The first is metals. Metals are any elements that are generally shiny, generally mean most of the time. They are shiny, they're solid at room temperature. There's one exception to that. We'll learn about that later. They're solid at room temperature. They're good conductors of heat and electricity. They're malleable, which means they can be flattened into sheets like aluminum foil can be flattened into sheets. And they are ductile, which means it can be bent or stretched. So you can be drawn into a wire. So you can take a big thing and you can stretch the metal out if you apply force to it, and it will make it be a wire, or you can bend it. That's ductile or malleable. They can be manipulated and bent. Okay, so these are just some very common metals. They're not always gray or silverish in color, but most metals are. Some can be kind of a shiny whitish silver, and then of course gold is gold colored. So they tend to be all shiny, various levels of shiny. And this is the good thing though, they're good conductors of heat and electricity. We'll talk about why at a later time. All right, then we have nonmetals. These are kind of the exact opposite of metals. You have metals and then you have the opposite of metals, nonmetals. And nonmetals are elements that are generally gas or brittle solids at room temperature. Not all nonmetals are gases, so it's not metals and gases, it's metals and nonmetals. So make sure you remember that. Carbon is a nonmetal, but carbon is not a gas. A lot of them are gases, but not all of them are. And if they are a solid, they're brittle. So like you hit them, they break, they shatter, they crumble. Think about like a charcoal briquette is made of almost entirely carbon. If you hit that with a hammer, it's going to just kind of break into a whole bunch of pieces. Whereas if you take a piece of metal and you smash it with a hammer hard enough, it's going to flatten. Nonmetals are poor conductors of heat and electricity. That's why we use nonmetals to wrap our metal wires in. The wires carry the electricity pretty well. The nonmetals that we wrap around them do not. And nonmetals tend to have a dull appearance, which means they're not shiny. They tend to be kind of just, flat, not really shiny unless you polish them up, which can be done. But that's nonmetals. They're kind of the exact opposite of metals. And so you have carbon. Phosphorus is kind of this reddish powder. It's actually what's on the head of a match. And sulfur, a yellow powder. Then you have metalloids. These are kind of the in-betweeners. They're not quite metals. They're not quite nonmetals. All right. They have some properties of both metals and nonmetals. They can be shiny, but they are also brittle. Like if you have a nonmetal or a metalloid that is a shiny metalloid, it's going to be shiny but brittle. So it'll kind of look like a metal, but when you hit it with something, or it'll break really easily. Silicon is an example of that, like what we make computer disks out of, computer chips out of. they're very, very brittle, hard things, not silicone, the rubbery stuff that is used in cookware and stuff like that that's flexible. But silicon, the element, is a very brittle substance. But metalloids are kind of a combination. So they could be shiny but brittle. They could be partially good conductors, but not malleable. And so there's a bunch of different things, but they're kind of in between. They're not quite metals. They're not quite non-metals. They're the in-betweeners. Okay. So these are some common metalloids. You have boron, silicon, arsenic, antimony, tellurium, germanium. It's actually almost all of the metalloids right here. There's not very many of them, but they're not very metallic. Yeah, I kind of lost my train of thought there. So let's move on. So those are the categorization of the elements on the periodic table here. And as you look at it, you'll notice that over here behind me, most of them, these on this side are non-metals, and most of these on this side are metals. And we will discuss the difference of those as we go on here. So in the 1700s, a guy by the name of Antoine Lavoisier published a list of all known elements of the time. And he simply organized them into categories of what type of element they were. And they had a little bit different categories for them. Back then, you had metals, gases, earths is what we would call non-metals now. But before Lavoisier did this, there was just kind of like some people had lists and all that stuff. He just kind of published a list of all known elements, and he organized them by what type they are. And it was kind of the first grouping of known elements. Now, at this time, there was only like maybe 20 or 30 elements that were known, because if you remember from our history of atomic theory, this was before Dalton's atomic theory. So it was before we knew about atoms and before they really started doing a whole bunch of experiments. Before this time, people or scientists were not really that concerned with chemistry per se. In fact, they were trying to do alchemy, which was trying to figure out how you could take a cheap metal like lead or aluminum and turn it into an expensive metal like gold or silver. So they were trying to do something like that. That was kind of the birth of chemistry. But at the time that Lavoisier published his list, there weren't that many elements known, and he just separated them in different types. So he had gases, metals, non-metals, and earths. And I just love the names that they have here. Light and heat. They thought they were gases. We now know that light and heat are energy and not gases. Dephlogisticated air. That's just a fun word to say. Dephlogisticated. And then phlogisticated gas and inflammable air. I looked up once what those two things were actually, what we call them now, but I can't remember what that was off the top of my head. Some of these names you would recognize because they're things that have been around for centuries. We've known about iron and copper and zinc and all these for quite a long time. So these don't have English names, so I don't know what they are in reference to. But this was Lavoisier's list. All right. So after Lavoisier did that was in the 1700s, and some time passed, and then Dalton comes around in the early 1800s, as we already discussed, and Dalton developed an atomic theory, and after Dalton's atomic theory, a lot of experiments were started to be done and started collecting data. And scientists started to say, hey, there might be something to this. And from that, they were able to discover a whole lot of other elements and learn about information about the elements that we didn't know before, like their masses and a lot of their properties and how to isolate them. And as they started to do that, they needed a way to organize all this knowledge, because when you have a whole bunch of data, you could just put it all in a page and it's really confusing. But if you want to look something up pretty quickly, you wanted to have something that is nice, concise, and easy to follow. And so they wanted to organize it in a way that was easy to use. So John Newlands proposed an arrangement where elements were organized by increasing atomic mass. At this point, they started to figure out that, hey, these tiny atoms have mass, and we can figure out what the mass is. And so we're going to use that atomic mass in order to organize them. So he organized them based off atomic mass instead of by type of element. So that was John Newland's. And when he did this, he noticed that when the elements were arranged by increasing atomic mass, their chemical and physical properties seemed to repeat in a pattern every 7 to 8 elements. So kind of like the music notes, A, B, C, D, E, F, G, A, B, C, D, E, F, G. If you're a musician, you know that those notes just repeat themselves. And one grouping of notes from A, B, C, D, E, F, G, A, that's one octave. All right, so it's 7 notes, and then the 8th one is an octave. So he called this the law of octaves, because what he noticed was element 1, the first element here, had certain properties, and then you go 7 elements, and then the next one had similar properties again. So hydrogen and fluorine had similar properties. So you had hydrogen, then lithium, and these, I can't remember what the original names were because these are not the current symbols for these elements. But you had all of these, kind of like the letter notes in the alphabet, notes in music, A, B, C, D, E, F, G, and then it repeats itself. All right. And so these two elements have similar properties. These two elements have similar properties. These two elements, and so on and so forth, every 8 elements. So he called that the law of octaves, oct meaning 8. All right, so a little bit later in the mid-1800s, a guy by the name of Lothar Meyer was the first to demonstrate that not only did there appear to be, but there actually was a connection between the element's mass and its properties. Its properties could help determine, or its mass could help determine some of its properties. So he arranged the elements into a table based on this increasing atomic mass. He didn't just group them, but he actually created a table where this is the smallest, and it goes in order, and then because what Newland's figured out was that just every 8 elements that repeated itself. So what Meyer did was he took that and put them into groupings so that they increased and all that stuff. It's very similar to the way we see it today. All right. Around the same time that Meyer did this, they didn't know it at the time, they didn't know each other, but Russian scientist Dmitri Mendeleev also created a table ordered by increasing atomic mass. So Meyer created a table based on its increasing atomic mass, but then Mendeleev also created a table ordered by increasing atomic mass. Now, before I go further, I want you to hear this. It's Mendeleev. Is Russian, so that's the way it's pronounced, Mendeleev. I mean, if you said Mendeleev, it's okay, but that's not the correct way to pronounce it. Anyway, at least not that I was told. So Dmitri Mendeleev created this table. Now, Mendeleev's table was able to do something that Meyer's table couldn't. Mendeleev was able to make predictions of the existence of undiscovered element. What Myers and Newlands did was whenever you had 2 elements that didn't quite fit the pattern, they just kind of crammed 2 elements into one little square on the thing so that the pattern would continue. Mendeleev, however, he left holes in his periodic table. So as he started to figure, he left holes. So you know, see that there's a question mark here and a question mark there, and there's question marks. So he left holes there because there was nothing there that we knew of, but he predicted that there was something that was there. And it had predictive power. That's the gold standard, if you will, of chemical or of scientific theories, is that they have the ability to make predictions of future discoveries. And that's what Mendeleev did. And that's why Mendeleev is known nowadays as the father of the modern periodic table. Even though the periodic table we have now is not the periodic table he had. This was Mendeleev's. And ours now is significantly different looking. It doesn't quite have the same look to it. He did things vertically instead of horizontally, the way we have things now. But he's called the father of the modern periodic table because his table had predictive powers. He was able to predict the existence of elements that we hadn't discovered yet. So what he did was he actually predicted the existence of 3 elements. I'll show you one right here. He called it ecosilicon. All right. He predicted that its atomic mass would be 72, its density would be 5.5, that it would have a high melting point. He predicted what its color would look like, that it would be dark gray. It would be attained in a a compound of potassium and fluorine. That's the ES there. It's K is potassium, F is fluorine. So he predicted it would be found in a compound containing those, that it would form an oxide with oxygen that would have a formula very much like that. The density of that oxide formula would be 4.7, and that it would be slightly soluble in hydrochloric acid. Those were his predictions based solely off of the properties of the elements that were around it on the table, but it was a hole in his periodic table. And so he said, okay, these elements have these properties, so, and these chemical properties and physical properties. So this new one that I'm going to call ecosilicon, which probably means something in Russian, is going to have these properties. Now, if you look at the table right next to it, you'll notice that germanium is the element that he was predicting. That's what we call it now. We now call it germanium. But the actual mass of germanium is 72.61. Its actual density, its melting point is 945 degrees Celsius. That's pretty high. It's a gray metal. It's found in potassium, a potassium fluoride compound. It forms what's known as germanium oxide. All right, it's got a density of 4.7, and it does not dissolve in hydrochloric acid at all. But when you look at it, these were his predictions, and these were the actual things once we finally discovered germanium. He was almost exactly correct as to what germanium is, and this is what he predicted. That's the power of Mendeleev's periodic table. That's what makes Mendeleev's periodic table so great, is that he was able to make predictions of the existence of elements. So it was from that that scientists said, hey, there's something to this, and we can actually then predict the existence and know. So now that we can predict the existence of an element, we know what to look for, and so we can go find it. And so from that, we had this explosion of going from like 20 or 30 elements to having 118 that we've discovered, all right, using the principles found there. Now, this was in the mid-1800s, 1850s. Now, fast forward 50 years, Rutherford and Chadwick discovered the nucleus, as we already discussed. They discovered the proton and the neutron. And so after the discovery of the proton and neutron, they found out that a better way to organize the periodic table would be based off of atomic number, because atomic mass, if you look at the periodic table really closely, in general, as the atomic number increases, the mass increases also. There are some exceptions, though, where if you order it based off of atomic number, the elements get switched. Or if you order it based off atomic mass, the elements get switched. And so we noticed that there was a difference, and that it could be better organized by atomic number. When you place it by atomic number, which at the time Mendeleev did it, we didn't know about atomic number because Mendeleev didn't know protons existed. So now that we know protons exist, and now that we know that protons are what identify the element, ordering it based off the atomic number means we have a whole lot more predictive power. And Henry Moseley was the guy who was able to show that connection. He was the one that was able to show that the atomic number worked better than atomic mass. And so when ordered by atomic number, Moseley discovered an even more clear pattern of repeating chemical and physical properties. All right. That periodic repetition, periodic means one every now and then, like you go to class one period at a time, and then you do the same thing. So Monday, you go first, second, third, fourth, fifth, sixth, seventh period. Tuesday, you do first, second, third. It's the same. It's repetition at given intervals. That's what periodic means. So the periodic repetition of chemical and physical properties when elements are arranged by atomic number is called the periodic law. So the periodic law says that if you order elements based off of an increasing atomic number, you will get a repetition in chemical and physical properties. And that is what we see with the periodic table. That's actually why it's called the periodic table, not just the table of elements. It's the periodic table because it's periodically producing new, or a periodic pattern of properties. Okay, that law led to the creation of the modern periodic table of elements. So Mendeleev's periodic table was predictive. It was great, but it's not what we have now. What we have now, the modern periodic table, was arranged and discovered based off of this periodic law. Periodic law, once again, is a law that says that as elements are arranged by increasing atomic number, their properties will repeat in a pattern. All right, so this is the modern periodic table that you are familiar with. You see it all the time. It's on the wall behind me. But I want to point out, you'll notice the color key here: metals, metalloids, nonmetals. So you'll notice all these blue ones are metals. The yellow ones are nonmetals. So hydrogen is the only nonmetal on the left side of the periodic table. All the other nonmetals are on the right side of the periodic table. And then your metalloids are the ones right in between. So it's kind of the transition between metal and nonmetal are the metalloids. And there's this thing here, it's called the stair-step line. It's what we actually call it because it's this little line on the periodic table that's shaped like stairs. All right, some periodic tables you'll actually see it a darker color. But you've got your stair-step line of your periodic table. And the metalloids are the ones that are touching that stair-step line, with the exception of aluminum. Aluminum is touching the stair-step line, but it is a full-on metal. So these are your things. Now, this periodic table is kind of old because it says that these are unnamed. They are named now, but I don't remember what the names are. This one has actually been discovered, so the table is filled all the way to room to 118 now. The time that this periodic table was printed, they weren't that way. Now, this is what it normally looks like. This is the way you've probably always seen it, but this is what it should look like if we actually organize things the way the properties and everything show us. This is what it should look like. We call it the wide version, and really the only reason why this periodic table is the way you see it all the time is because this version does not fit on a page in a book. In fact, if I were to print this in a book to fit on a page in the book, then it would be so small you couldn't read anything, right? Or if you make it to where the stuff is big enough for you to be able to read it, then you're going to have a fold-out page in the book. And some of you may have seen books where there is somewhere in there a middle in the page that folds out in the middle of the book. Well, that's more expensive to make. And if you're making textbooks and you're making a whole lot of stuff, you don't want to spend more money to make something. So they devised the idea of taking these two groupings of metals that are in the longer version, the wide version. That's these guys right here. They just separated them out of the table and then squished these two parts of the table together. And so that is what the modern periodic table looks like. Now, what we're going to be doing moving forward after this, so that's the brief history there, and go back and watch it again. You need to learn what Newlands did, Meyer, Mendeleev. Those are the three main guys. Lavoisier made a list. John Newlands discovered the repetition in properties and created the law of octaves. And then we had Meyer and Mendeleev, who both made a table based off of increasing atomic mass. However, Mendeleev's periodic table was able to make predictions of future elements and undiscovered elements. So that is the brief history of the periodic table. In the next set of notes, we are going to discuss how it is actually arranged and a few other things about the elements in the periodic table. So look forward to that.